Greetings everyone. Let me start by thanking the organizers for putting this exciting symposium together. And in today's talk I'm going to talk about our recent work on spinels, in particular discovery and design rules of novel double spinel chemistries that can be formed by combining two single spinels. Since their discovery more than a century ago, spinel oxides have found their way into many aspects of science, technology and our everyday life. Possibly the single most important feature of spinels is their diversity in cation chemistries, coming from the fact that synthesized spinels contain most of the main group and transition metals. By playing around with the cation chemistries at different coordination environments, one can tune their electronic, optical, catalytic and magnetic properties. This diversity and tunability in the properties makes spinels useful in a variety of applications, some of which are highlighted on this slide. Spinel oxides are typically represented by the formula AB2O4, where the oxygen ions form a cubic closed packed sublattice and the A and B cations occupy 1/8 of the tetrahedral and 1/2 of the octahedral sites, respectively. The most commonly occurring spinel structure is termed as the normal spinel configuration, where the A cations occupy the tetrahedral site and B cations appear on the octahedral sublattice. The cation ordering in the ground state of some of the spinels is reversed from the normal. These are called inverse spinels, where the tetrahedral site is occupied by B cations, while the octahedral site is shared by the A and B cations. Some prototypical examples of compounds with normal and inverse ground states are shown here. At finite temperatures, the cations on both the tetrahedral and octahedral sites in a spinel structure can start to mix, giving rise to cation disorder. There are two different types of order disorder phase transitions that can occur in spinels. For the inverse spinels, there are two different cations on the octahedral sublattice, and generally near the room temperature they exhibit an order disorder phase transition. An example is shown on the top right, where the Warren-Coley order parameter can be seen to change as a function of temperature. This order parameter essentially tracks the second nearest neighbor cation distributions on the octahedral sublattice. For the perfect ordered state, it is 0.25 and 0 for a completely random configuration. This octa-octa transition cannot change the inversion. At this critical temperature, inverse spinel goes from an ordered inverse to a disordered inverse configuration. As the temperature is further raised, a mixing between the octahedral and tetrahedral sites starts taking place. At this point, the degree of inversion x starts changing. At a finite temperature T, x is essentially defined as the amount of B cations appearing on the tetrahedral sublattice. It is 0 for the normal case, 1 for the inverse case, and 2/3 for the completely disordered spinel case. In last several decades, a lot of work using both experiments and theory has been devoted to understand different factors governing the tendency of a given spinel chemistry to adopt a normal or an inverse ground state configuration, as well as to understand their finite temperature, order disorder phenomena, and cation distributions. But I'll not have time to go into all those details. Instead, in this talk, we are going to focus on double spinels, that is, stable ordered configurations reached by combining two single spinels. To address this question, we start looking at a set of prototypical spinel compounds, namely magnesium aluminate, magnesium gallate, and magnesium indate spinels. As we go from aluminum to gallium to indium, the thermodynamic tendency to adopt the inverse configuration is known to increase systematically. At the room temperature, magnesium aluminate is a normal spinel, magnesium indate is an inverse spinel, and magnesium gallate is a mixed spinel exhibiting an intermediate degree of inversion. We start by confirming that these well-known notions are captured well within our computational approach, as shown in the table above. Next, we pairwise combine the three single spinels to form double spinel configurations. The three cases are shown on the bottom left. For a given double spinel, there are more than 160,000 unique configurations that can be enumerated within a 28-atom supercell. Since calculating the relative energetics of all possible structures using DFT computations is clearly impractical, in this case we resort to a cluster expansion based effective Hamiltonian approach. We use cluster expansion approach implemented within the COSM code. Once the effective Hamiltonian model is developed and validated, we use Monte Carlo simulations to study the finite temperature behavior and cation order disordered phenomena. Here are some more details on our computational approach. We start with a small randomly selected set of configurations for DFT computations. A cluster expansion model is then trained on this set. Within this formalism, the energy E of a configuration is expended as a linear combination of pseudo-spin configuration variables. The coefficients VI's represent effective cluster interactions that are fitted to the DFT energies using a 5-fold cross-validation method. We then iteratively refine the model until the entire convex hull is mapped with no new configurations predicted to be near or on the convex hull, and the desired predictive accuracy of the cluster expansion model is reached. The trained cluster expansion model is then utilized to efficiently compute the partition function, free energy, and other thermodynamic properties. So without further ado, let's take a look at the final results. Interestingly, the predictions from the cluster expansion model suggest that there is not a single order double spinel compound that is thermodynamically stable for the magnesium aluminate, magnesium indate, or magnesium gallate, magnesium indate mixtures. In both cases, all the double spinels have a higher energy relative to the respective two single spinel endpoints, indicating that in these cases any order double spinel structure is going to decompose into two single spinels, regardless of their relative mixing compositions. This is somewhat surprising for magnesium gallate, magnesium indate, as both of these compounds are inverse spinels, and conventional wisdom would suggest that two inverse spinels could actually mix. But in this case, if they do, our results suggest that it would be driven by entropy, not enthalpy. More excitingly, for the magnesium aluminate, magnesium gallate case, we predict a special configuration reached by equimolar mixing of the two single spinel compositions. This composition has a significantly negative enthalpy of mixing, which is on the order of the stability of the inverse structure of magnesium gallate relative to the normal spinel structure. Interestingly, this is the only compound that appears on the convex hull for the entire range of compositions and has the same space group as that of the inverse spinel structure. To the best of our knowledge, we are not aware of any previous reports of such an order double spinel over the entire spinel chemical space. In fact, it was somewhat surprising to us to find out that a normal and inverse spinel could mix together to give a thermodynamically stable ordered configuration, because in many cases a normal and inverse spinels are known to not mix. As an example, at the operating conditions of a nuclear reactor, the corroded steel is often characterized by an oxide bilayer structure, mainly comprised of two spinel structures materials, magnetite Fe3O4 and nickel iron chrome spinel. Interestingly, this bilayer forms because different levels of inversion in the two spinels lead to immiscibility. Our results on the magnesium aluminate and magnesium gallate mixing, however, indicate that this is not a general behavior and that a normal and an inverse spinels can actually mix. As a next step, we study the finite temperature behavior of the predicted double spinel compound. The computed enthalpic and entropy contributions to the free energy as a function of temperature are shown here. While below 300 Kelvin, the ordered double spinel configuration is preferred. Mixing between magnesium and aluminum on the octahedral sublattice starts above this temperature, leading to a random inverse-like cation configuration. This mixing results in relatively small entropic gains, which are reflected in free energy profile shown in the inset. It can be seen that mixing on the octahedral sublattice has little impact on the enthalpy of the material. Further increasing the temperature beyond 500 Kelvin sets off intermixing between the disordered octahedral and the tetrahedral sublattices, allowing gallium to appear on the octahedral sublattice. As a result of this inter-sublattice mixing, the induced local strain effects lead to a sharp increase in the mixing enthalpy, while the configurational entropy also rises abruptly. As a result, the fully ordered compound is not stable once temperature is introduced, but some level of ordering is still maintained at high temperatures. We also note that for magnesium aluminate, the tetrahedral octahedral mixing temperature has been reported to lie between 750 and 930 Kelvin in different experimental studies. For the inverse single spinels magnesium gallate and magnesium indate, the corresponding values are relatively higher, 1100 Kelvin and 1300 Kelvin respectively. It is interesting to note that double spinel exhibits a tetrahedral octahedral mixing temperature which is significantly lower than the reported for closely related single inverse spinels, magnesium gallate and magnesium indate. This lowering of the critical mixing temperature can be traced back to the availability of unique cation mixing options such as gallium on the tetrahedral site and aluminum on the octahedral sites that are not available in the single spinels. To validate the theoretical predictions, we have synthesized the predicted double spinel compound via ball milling. EDS was used to confirm the homogeneous dispersion of cations within the material. The EDS characterization results on the top left indicate that the material exhibits micron-scale homogeneity of elemental distributions. Furthermore, the synthesized single-phase compound reveals a chemical composition of the individual elemental species aligned very well with that of the magnesium aluminum gallium O4. The XRD results highlighting cation ordering and evolution as a function of annealing time are presented at the bottom, where XRD patterns for the compound are shown as a function of anneal time for two different temperatures, 473 Kelvin and 773 Kelvin. These results immediately highlight a challenge in validating the theoretical predictions. At the low temperatures at which the ordered magnesium aluminum gallium O4 structure is predicted to be stable, the kinetics are simply too sluggish to form that structure. That is, at 473 Kelvin, we see no evolution of the structure of the compound over a period of time as long as for 6 weeks. To overcome kinetic limitations, we anneal the material at 773 Kelvin. At this temperature, we do not expect to be able to form the fully ordered double spinel structure, but we do expect the material to exhibit significant order and to be more ordered than the starting material synthesized at 1773 Kelvin. This is borne out by the evolution of the XRD pattern. As time progresses, the 331-220 peak ratio are much closer to the ordered case than they are at the beginning of the anneal. We do not claim that fully ordered structure has formed, but rather that the material is evolving towards the low temperature ordered structure. While not serving as a direct confirmation of the theoretical predictions, the XRD analysis of the annealed material does indicate the strong ordering tendency of the compound. The next question is that, are there any other possible double spinel chemistries? To address this, we consider mixing of all possible normal and inverse spinel compounds that have the A cation in common. Since there are 3 cations and 3 lattice sites, 1 tetrahedral and 2 octahedral in a double spinel, There are three different configurations that are possible. We call these double spinel inverse of type 1, double spinel inverse of type 2, and double spinel normal, represented by ds inv sub 1, ds inv sub 2, and ds norm, based on their similarity with the parent single spinel configurations. Here are some more details of the double spinel chemical space that was explored. In total, we considered mixing between 49 normal and 22 inverse spinels that have been experimentally synthesized and have a cation in common, generating a set of 92 double spinel compositions. We performed DFT computations for the entire set of 92 spinels in three different double spinel configurations shown on the top right. Our results show that out of these 92 cases, the inverse double spinel configuration of type 1 is of lowest energy in 48 cases, normal double spinel configuration is of lowest energy in 42 cases, and there are only 2 cases where inverse double spinel configuration of type 2 was of lowest energy. Out of the 92 spinels, 49 were found to be thermodynamically stable with mixing energy of less than 0 eV. One should keep in mind that the reported double spinels are thermodynamically stable, which is the initial requirement of these compounds to be synthesizable. At finite temperature, the kinetics would have the major influence on the synthesis of these double spinels, but that is something we cannot probe using our computational methodology. A distribution of different cations occurring on the tetrahedral and octahedral sublattices of these double spinels is also shown on the bottom right plot. Next, we focus on understanding physical factors that dictate whether a double spinel chemistry formed by combining two single spinels is likely to adopt an inverse or a normal double spinel configuration. We start by exploring simple correlations between various elementary features of the different elements forming the double spinel with the DFT calculated energetics. This exploratory analysis provided strong indications that local coordination environment dependent relative size effects of different cations going from single to double spinels play an important role in the stabilization of the double spinels. To illustrate this with a concrete example, here we plot the absolute differences of Shannon ionic radii for the tetrahedrally coordinated A and B prime cations in a given double spinel against the DFT calculated inverse double spinel mixing enthalpies over the entire range of the dataset. The rationale behind choosing the specific cation radius stems from the fact that while A cations occupy the tetrahedral sites in a normal spinel, in a double spinel inverse configuration all the fourfold coordinated sites are occupied by the B prime cations. Therefore, if Shannon's ionic radii for the A and B prime cations differ significantly, one would expect that the resulting double spinel chemistry would be destabilized due to unfavorable local strain effects. Indeed, from the plot it can be seen that most stable inverse double spinels, shown in red, exhibit a relatively small value of radii difference, whereas for the unstable chemistries with E mixing greater than 0, shown in blue, a rough linear trend of E mix with the radii difference is seen. Although such qualitative notions indicate the importance of local strain effects on the tetrahedral sublattice in the stabilization of a particular double spinel, effects related to local strains on the octahedral sublattice and/or factors other than the local strain effects might also be important. To systematically explore these factors and to identify a simple and physically intuitive descriptor for classifying the double spinels, we employ the SISO approach based on the compressed sensing technique. This approach allows for efficient exploration of vast descriptor spaces, with the number of unique descriptors typically reaching up to several billions, and has recently been applied to a number of materials design and discovery problems. To generate a classification model for predicting the relative stability of a double spinel chemistry in double spinel inverse versus double spinel normal structure, we start with a set of 6 Shannon's ionic radii and one categorical variable defined as SCL, where SCL stands for spinel classification label. We consider both the tetrahedral and octahedral coordinated ionic radii for each of the three cations. SCL not only labels the 2, 3 and 4, 2 type cation charge states for the double spinel, but also distinguishes whether the cations on the octahedral sublattice exhibit a uniform nominal oxidation state or not. Starting with these 7 primary features, the SISO method enumerates a large set of features by iteratively applying a set of pre-specified algebraic operations on the current feature space. This iterative procedure leads to a truly vast set of descriptors of increasing complexity via combinatorial explosion. In the most complex subspace phi 3, we have nearly 1 billion derived features or descriptors. As a next step, to identify the best set of descriptors for the classification problem at hand, the SISO method employs the Shor independent screening (SIS) method, followed by a sparse solution algorithm using sparsifying operator SO. Here L0 was used. Starting with the accumulated set of feature space, the SIS method selects a subspace of features with the best classification performance quantified via targeting an overlap region in the classification space with the least number of samples and a minimum surface area. The SO approach then evaluates all possible combinations of features from the SIS subspace, yielding the optimal solution. In the present case, a SIS subspace of 1000 was consistently used for identifying the best two-dimensional descriptor pair. The classification achieved with the best descriptor pair identified with the SISO approach is presented in figure shown here. The inset depicts a magnified view of a very small overlap region formed by the convex hulls of the two double spinel types, namely the double spinel inverse 1 and double spinel normal, identified with the blue and red markers respectively. The area of the circular markers in the figure represents the magnitude of the relative mixing enthalpies between the two double spinel types, and therefore provides a graphical depiction of their relative stabilities. To gain a deeper insight into the excellent classification performance, next we take a closer look at the various terms constituting the identified descriptor pair D1, D2. We divide each descriptor in two terms as shown here. The second terms identified for both descriptors D1 and D2 can be visually recognized to be largely dominated by size effects, the original premise that motivated the descriptor analysis in the first place. It is also interesting to note that these terms share a common expression underlined with a blue line, which essentially captures relative local strain effects caused by forming a double spinel by combining two single spinels, one normal and one inverse. The role of the first term is a bit more difficult to comprehend just by a visual inspection alone. Upon plotting each of these two terms, it becomes clear that both terms play an identical role in the construction of the two descriptors. They essentially separate the double spinel chemistries based on their cation electrostatics, i.e. normal double spinels formed by 2,3 versus 4,2 cation oxidation states. Naturally, the categorical feature SCL plays a dominant role in these terms. This analysis provides a transparent understanding of the identified descriptor pair, showing that interplay of both strain and electrostatics drives the energy differences between the cation orderings, and whether a double spinel is inverse or normal in nature. To summarize, we used both theory and experiments to identify the existence of a double spinel magnesium gallium aluminum oxide formed from mixing an inverse spinel and a normal spinel, and studied its finite temperature properties using Monte Carlo simulations built on a cluster expansion based effective Hamiltonian model. Next, we used high throughput DFT computations to explore a vast set of double spinel chemistries to identify 49 thermodynamically stable double spinels and studied their electronic structure. Finally, using only cation specific properties, We employed machine learning to successfully classify the double spinels via their cation orderings, showing that an interplay of both strain and electrostatics drives the energy difference between the different cation orderings. The discovery and identification of these novel compounds provide a unique opportunity for designing materials with new functionalities. I would like to end by acknowledging support from BES, and thanks for your attention. I'm happy to take any questions.